Okay, guys, let's go ahead and get started. We're going to continue with deep neural nets or neural networks, and I will not be uploading last lecture. There were a few hiccups in it. I'm just going to record this one, which will be almost like a replication of what we did last time. So let me go ahead and share my screen. Okay, so just recall that we learned how to compute the errors at each layer in our given network from our last lecture. And this was our last slide here. So we input a given feature vector. Then for each of the layers, excluding the first layer, which is our input layer, we calculate the pre-activation and then the post-activation at each layer. This is called the feed-forward phase. After we calculate the pre and post activations at each layer, we then calculate our output error. And recall that our cost function is the sum of the square differences divided by 2. So we calculate our output error, which is given by the derivative of the cost function with respect to A, or the gradient of the cost function with respect to A, Kronecker product, or entry-wise product, with the derivative of our activation function, which we chose to be the sigmoid function, applied to the pre-activation values at the last layer. So once we have our output layer, our output error, we then back propagate this error through the network. So for our layers L-1, where L is the number of layers, all the way to our second layer, again, we exclude the first layer, we're going to calculate the errors at each of the layers. And that's given by this Kronecker product here. Right? So once we have these errors, then as we saw in the last lecture, the gradient with respect to the weights and the biases is just the errors at that layer and that node or neuron times the coefficient of the weight or the bias. So in terms of the weights, the coefficient was the activation, the post-activation at the previous layer. That was the coefficient of the weight at that layer. So that's why we have that term appearing with the error at that layer. And then the coefficient of the bias was 1, so it's just 1 times the error there. Okay, so now to optimize our weights, we're going to use mini-batch gradient descent. So we select a set X of M training examples. And then for each training example in our mini-batch, say Xi, we set the corresponding first layer activation, post-activation, equal to our input, right? So this is our input layer. And then once we do this, we then do the forward pass or feed forward. And then for each of our layers, we're going to calculate our pre-activation and our post-activation here, right? So the pre-activation is a linear combination of the weights times the post-activation in the previous layer plus our biases. And then our post-activation at that layer is just a sigmoid function applied to each of those values. Okay. So then we output our error as before, and then we back propagate our error. So once we have found the errors, and notice that the errors now are with respect to each of the X's in our mini batch. So we have to save all of these when we program this, right? So we're gonna have to feed forward, feed forward, feed forward for each of the training examples, and then back propagate, back propagate, back propagate for each of the training examples. So we're gonna have, for each training example, we're going to have a delta vector, okay? So once we have these, then we can use gradient descent on each of the layers and update our weights and biases at each layer. So the weights at layer L, and this is from the last layer up into the second layer, we're going to just sum the values. So basically this is summing the partial derivatives, right? And then we multiply by our, here, the alpha there is our learning rate, and then we just divide by m, the number of training examples. So it's, what this is saying is like the average gradient over all of those training examples, we're going to take the average of that, and that's going to be our descent direction. And then the same thing with the biases. We have our average bias over all of the training examples in our mini batch, and we're going to say that that's going to be, or no, the average gradient over every training example in our mini batch, and then we're going to take a step in that direction with this learning rate or step length. Okay, so now let's go to the coding aspect of this with respect to the MNIST dataset. Okay, so recall from last time that our MNIST dataset is a collection of 70,000 handwritten digits, 60,000 of which are what we will use as our training examples, and then 10,000 of the images are what we will use for testing. So when we train our network and we use gradient descent, our mini batches are going to come from the 60,000 training examples, and we're never going to see the 10,000 testing examples. That's for after we've trained our network, and we want to see how good we're performing. So let's go ahead and import this data set, right? So we can do that using ML datasets. So using ML datasets, that will give us access to this data set. And then we're going to want to look at these images just because I like to. Using images, using test images. And then we're going to want to plot things eventually, so using plots. Okay, so when you call these image packages, you might have to download or install Image Magic IO using the package manager in Julia. So just keep that in mind, that these might give you a little bit of headache when you're installing them. So you might just have to do the full Image Magic IO, which contains these other sub packages. So we're going to say that train X, train Y is equal to MNIST dot train data. Okay, so this is going to return a tuple of the features, the feature measures, and then the corresponding label, whether or not that you have a digit 0 through 9. Okay, so then I'm going to have test X, test Y, and that's going to be MNIST dot test data. Okay, so that's going to take a second to run. Okay, so this data set here, the X, the train X and the test X are what are called tensors. So tensors are multi-dimensional arrays. So for example, a matrix is a 2-dimensional tensor. This is going to be a 3-dimensional tensor. And you can think of this as like each slice of this box is a matrix. And each matrix is going to represent the features of a given image. So let's go ahead and say, let's just look at the size of train X. So this is a 28 by 28 by 60,000 tensor. So what that's saying here is that we have 28 entries along the rows here, 28 entries along the columns, and then there's 60,000 of these matrices. Okay. And each of these corresponds to a matrix representation of a grayscaled image of a handwritten digit. So see the 28 by 28, that's each matrix. So each of these images is a 28 by 28 matrix. And these are all values in the range 0 to 1. And that just represents the pixel intensity of that given pixel. And again, these are very low res images. 28 by 28 is not that much, but it still captures the image well. And if we wanted to look at an example, so we just do train X, and then we'll say all the rows, all the columns, and then we'll look at the first matrix. Okay, so we see that we have a 28 by 28 array. In this array, or this matrix, represents the feature values for this image, the pixel density for that image. We can say, well, what does this thing look like, or what does the image look like for this thing? So we can use, it's called color view, okay, in grayscale, and we'll just pass in that instance. So train X, all the rows, all the columns in the first matrix in that data set. And then we can also print the label, the first image in our train data is labeled, and then we can just pass in train Y, which is its label, 1. Okay. And we're calling color view for the first time. Oh, so you can see that it doesn't look like a 5. That's because we need to rotate this or transpose it. So there's the little transpose symbol there. So we see that that's a 5, and it's labeled 5. Okay. So each of these training features, or each of these instances of training features is a matrix. But as you recall, our neural network is going to take in a vector. So we need to take this thing right here, and we need to make this into a vector, okay? So one way that we can do that is by saying, let's just call the function, I'll just show you, it's called reshape train X, all the columns, all the rows, all the columns. So the first matrix in that data set. And if we multiply 28 by 28, we'll see that there's going to be 784 entries in there. So that's what we're going to do. So let's just see what this does. So you can see that this makes a column vector, right? So what this does is it just takes the entries in here and it just stacks them on each other. So it takes all the data here is indeed contained in this column vector. So what we're going to do is we're going to go ahead and take every instance in train X and we're going to convert it to a column vector. So we can do that. So I'm going to say X is going to be our column vector, our matrix of column vectors. And then Y is going to be our one-hot encoded label vectors. So we can say for I equals 1 to length of train X, and train Y is going to have the same length. We can say push into X, the reshaped or the shaped train X. So all the rows, all the columns, I. And we know that each of those is going to be a 784 entry column vector. So we're just putting all those things in X. Okay. And then now, so each of the labels is an integer value between 0 and 9, because every digit is between 0 and 9. So we need to take those and pass those into a vector where the ith entry corresponds to the label. So the way that I did this, and there could be better ways, is I just start with a 10 entry vector of zeros, and then I say that y of train y I, because that's corresponding to the label that that's the corresponding label to the feature vector that we're looking at. And since indices start at 1 in Julia, I'm going to say that 0 is going to be in the 1 place, 1 is going to be in the 2 place, 3 is going to be in the 4 place, so forth and so on. So I'm going to say that that 0 entry now is going to be equal to 1.0. Okay? And then I'm going to push that into y. And then I can end that for loop. And then I can say the train data is going to be equal to the tuples x for x and zip x comma y. So that just gets my data ready to pass into a neural network. So once I do this, I can just say, okay, copy that. And then I'm going to do the same thing for test now. So our test data, it's all in the same format. Okay, so I just reinitialize there. Okay, so then this will be test data here, like that. Right, I don't want to see all those entries, so. Seems to be, so I know there's 60,000 things in here, so let me just do, oh, I know what it was. Here, there's only 10,000 things in the train, so train. Oh, here. Train. Oh, no, this is, that should be test. That doesn't work, I'll just, so train, test, test, test. Yeah, I'll just do this. I know there's 10,000 things in there. I know that there's 60,000 in there. Okay. So that just gets our data ready to go. So now let's go ahead and build our neural network. So recall we're going to use the sigmoid function as our activation function. Pre-activation is just the weights at the current layer times the post-activation at the previous layer plus the biases at that layer. And then the activation at that layer is just a sigmoid function applied to each of those. So what we're going to say here is that we need to define our sigmoid function. So sigma tab of value x is equal to 1 divided by, or it's always good to do that. So 1 divided by 1 plus e of negative x. And then the derivative of the sigmoid function is just defined as follows. So d sigma of x is equal to sigma of x times 1 minus sigma of x. Okay? So it's not hard to show that this is indeed the derivative of this activation function. Okay, so the way that I would like to initialize our neural network is as follows. So this is something that you probably haven't encountered before. So let me just make some comments here. Define the activation function and its derivative. So now I'm going to define a neural network object. So, or maybe I shouldn't say object. So a neural network type. So Julia, unlike Python, is a functional programming language, and it's not object-oriented. You can't really define your own objects, but you can define your own types. So the way that we can do this is by using a struct. And since our neural network is going to change over time, it's going to be what's called a mutable struct. And it's going to be called a neural network. Okay? So then what is going to be passed into this neural network? What are its properties or attributes? Well, it's going to have a weight matrix, okay, and a bias matrix. So all the weights will be stored in W, and all the weights and all the biases will be stored in B. Okay. So we have that. So, and I'll show you how this works in a moment. Next, let's initialize our weights and biases. So I'm going to write a function to do this. I'm going to say function create network, and it's going to take an input layer size, okay, and then the hidden layer sizes, and then finally output. Yeah. Output layer size. And that's all you need to input to figure out how to form your neural network. Once you know your input layer and your hidden layer size and your output layer size, then you can construct the weights and biases accordingly. So what we can say is that W is going to be, so there is no there are no weights at layer 1, the weights start at layer 2. So that's what I'm going to do. So I'm going to say rand from a normal distribution, hidden layer sizes 1, comma, and then we want this to have input layer size. Okay, so this is going to make a matrix of weights from a random normal distribution where we'll have this many rows and this many columns, which is exactly what we want. And then the same thing for the biases. So there are no biases at layer 1, so I'm just going to put in a dummy entry there. And then I'm going to have a column vector of hidden layer size is 1. Okay. All right, so now I need to construct the weights for the hidden layers. So what we just did is we made the weights here and the biases here. So now we need to construct the weights for all the other layers. And this is an array of integers that represent their sizes. So what I'm going to say is for I equals 2 to well, we can say, yeah, the length of hidden layer sizes. We can say push into W a random normal distributed matrix. So hidden layer sizes I, comma, hidden layer sizes I minus 1. So this will have hidden layer size, so 2 to rows, and then hidden layer sizes 1 columns for the first one, and it keeps on going all the way through. And then we need to also make our biases, so push into B. A column vector with this size here. So hidden layer sizes I. Okay. Okay. So then this constructs the weights and biases for the inner layers, and then we need the final layer right here. So I'll say that push into W. Again, we're going to have output layer size, comma, hidden layer sizes the end. And then push into the bias vector, it's a column vector with that many output layer size. Okay, and so we have our mutable struct here, which is a neural network, and we're going to say turn a neural network type that takes in W and B. And these don't have to match these, you just have to pass them in this order. So whatever you pass in there is going to be given that assignment, and then whatever you pass in there will have that assignment in this object, or this type. Okay? All right, so let's see if this works. So we can say maybe neural net is equal to create network. We'll say it has an input size of 784 because that's how big our first layer is. And then we'll have it maybe 100, 100, 100 for the hidden layer sizes. And then our output is going to be a 10 dimensional column vector that corresponds with these one hot encoded label vectors. So let's see what this looks like. Oh, that's not good. Should put an equal there. Okay. So now if I want to access the weights and biases of our neural network, we can say NN W. That's a huge 5-element array where these are the weights at the second layer, weights at the third, weights at the fourth, weights at the output. And then neural network.b, biases at the second layer, biases at the third, biases at the third, fourth, biases at the last. Right? And you can see 1, 2, 3, 4, 5 layers, right? So, okay, so this is, we've created a neural network, and it's going to store our weights and biases. Okay. And we can, I guess if you want to look at the dimensions of the network, we could do something like this. For weights in our weight matrix, so we have 784 to 100 to 100 to 100 to 10. And that's what it looks like. Okay, so now we need to define the forward pass, right? So if you recall, we need to compute the pre-activation and post-activation at each layer. So let's just write a function to do that. So function forward pass, and that's going to take in a network, a neural network, and then it's going to take in a training instance, and that's all it needs to take in, right? You just pass a training instance into a neural network, and then you compute the pre and post activations at each layer. So recall there is no pre-activation at layer 1. So the Z's are going to be the pre-activation, and the A's are going to be the post. So the post activation at layer 1 is precisely your training instance. Okay, so training instance 1. So our training instance is a tuple, and the 1 entry is the feature vector that we need to pass in. Okay, so for I equals 2, to, let's say, the length of our weights, because that's the length is going to be how much. So, for example, 1, 2, 3, 4, 5, right? So that's how many layers there are. So the length of our weights is exactly the number of layers. So the length of network dot weights. Okay. I'm going to push into Z. So network dot weights at I times our post activation at the previous level, previous layer. That's a -1 there, plus our biases at that layer. Okay, and then we're going to push into our post activation collection A, sigmoid. So sigma dot, which is broadcasting. It's going to apply the sigmoid function to each entry in Z. So Z I. Okay, so if we return Z and A here, we've successfully forward passed a given training instance, and we found the pre and post activation values at each layer. Right, so once we have that, the final post activation, so the final post activation in A, right, is our output vector, and we can use that to make a prediction as to what the label is. So function predict, and this is going to take in a network and a training instance. And we just need to say, something like the A equals to our forward pass with the network and a training instance. And then the very last vector in this matrix here, or this array, is our what we want. So we can say return our max, which is the index with the highest value in A. So the index corresponding to the highest value in A, or the very last vector in A. And then -1, because that, remember we added 1 to the actual label to get what it was, so we subtract off to make a prediction. Okay. Right. So, so now once we have a prediction, we can write a function to test how accurate we are. So function success percentage, and that's going to take in a network and a data set to test it on. And we're just going to return a string representation of how accurate we are. So string. So the percentage of correctly classified images is, and then we just take, so the string is going to convert whatever we put here into a string, and we're just going to sum predict network, and then x, so we're summing in x. So we ask if that's equal to our max of x, 2, which is the label. So x is just something in dataset. And the second entry in that tuple is the label, which is a column vector where the 1 is, where a 1 in the ith entry means that the data is labeled I minus 1. So does that equal? If it does, return a 1. Otherwise, return a 0 for x in data set. And then close off that string. So hopefully this works. So maybe we can just test it out. Success percentage on the network we defined above. And then we'll say test data. Oh, if this is going to be a percentage, I don't know what I was doing here. So we need to take this sum and then divide it by the length of the data set, and then times 100 to just move the decimal place over. I kind of want to put a percent sign there now, so I'll just do that here. Oh. Oh, there should be a comma. Yeah, so there it goes. So that's kind of interesting. Even with these randomly chosen weights and biases, we're already at 11% accuracy, but okay. So next, we need to calculate the output error and the hidden layer errors at each layer. So I'm going to do that. So function, I'm going to call this error deltas. And that'll take in a neural network type and a training instance. Okay. So I'm going to say Z and A. We need to calculate the pre and post activation values at each layer in order to do this. And we can do that using our forward pass function, network, and a training instance. And now we're going to say that delta is going to be our array of vectors that represent the output error and hidden errors. So we can say that the first one in here, I'm going to say, is going to be equal to a end minus training instance 2. So this is the output vector, and this is our column vector. So these are both 10-dimensional column vectors. And this is our output, and this is our label. So this is the derivative of the cost function with respect to A. That's exactly what this is right here. And then we're going to broadcast that. So dot times means that each entry here is being multiplied with each entry, each respective entry in the next vector. So dot times d sigma, so the derivative of the sigmoid function, broadcasted on Z end. Okay, so this is the Kronecker product of the derivative of the cost with respect to A times the derivative of Z at the last layer. Okay. Okay, so now we need to populate this with the errors at each layer. So I'm going to say for I equals, say, length of network.w, right? So that's like, now I'll go ahead and write this so it looks more like our notes. I'm going to say L is equal to that. So that's the number of layers. So here, for I equals L minus 1. We're going to decrement by 1 and then go down to 2. And then we're going to push first. So this is going to put whatever so push first into delta. This is going to put into delta in the first entry. Okay. So we're going to say network dot W of the weight at the previous layer transpose times the derivative of the sigmoid function. Oh no, sorry. We can say delta of 1. So delta of 1 currently is the end, right? You see that. So this is the output error at the end. And delta 1 is always going to be the errors at the previous layer because we're pushing first, right? If we're always going to push into this, as soon as we calculate errors, it goes into the first entry. So when we're calculating errors at the previous layer, we always call the first entry of delta. And if you recall from our slide, that's how it works. So W at the WL plus 1, the errors at L plus 1, Kronecker product, sigma prime at that given layer. So this is always going to be, as we're running through this for loop, it's always going to be at the very first entry. So that's why I put a 1 there. So that, and then Kronecker product, or dot times d sigma of zi. Okay, so that should match up. Okay, and we do that all the way down to 2 because there is no error at the input layer. And then just because I want this array to have a kind of dummy entry in the first, at the index 1, I'm going to say that push first into delta, just a dummy entry. And then I'm going to return A comma delta. So we have our post activation and our errors that this returns. All right, so let's check it. So error deltas. We'll pass in the network we've made above, and then we'll say train data 1. There's an error somewhere. It's probably a missing parenthesis somewhere. Hold on 1 second. L is just that. Yeah, I guess I just was missing This is exactly what I just typed in, except for this is a little bit different, but that shouldn't have made a difference. I think I was just missing a parenthesis somewhere. So these are our error deltas. So we can even, this is an array. So um, like a test delta test is equal to this. And then we can just say like, what do these things look like? So delta test end, what does the end look like? And it should be 10, right? Because our output is a 10-dimensional vector. So at those neurons, the error should be, there should be 10 of them. All right, so now we've gone through that part. It's time to do gradient descent. So in order to do this, we're going to use stochastic mini batch gradient descent. So I'm going to write a function to make a random mini batch, and it's going to take in mini batch size, and then a data set to work on. Okay, so I'm just going to say that k is equal to some random integer between 1 and the length of data set minus the mini batch size. And you'll see why I do that in a second. And then we're going to return data set from k to k plus mini batch size. So what this is saying is like this random k, it's not going to be too far into the data set because I want to have, so if this was like m, I want m things in here. So I start at k and I add m. And if k was too big, I would add m and I would get something that wasn't in data set anymore. So that's why I subtract off right there. Okay. Okay, so now that we have that, we can write a function to do the mini batch update on our network. And I'm going to use an exclamation point because this is going to be a modifier. It's going to change the network that we pass into it. So network mini batch size, and then a data set that we want to train on. Okay, so I'm going to say batch is equal to make random mini batch, pass in the network, and then pass in mini batch size. And then say L is equal to the length of network.w. Okay. So then, as before, we need to get our error deltas. I'm just going to copy this and paste it. So let's call this A test. All right, so once we have that, we can say for our batch, like we need to calculate each of these for our batch. So what I'm going to say is a batch is equal to so empty, and then delta batch is equal to empty. And then I'm going to push these into, so push into a batch A. So that'd be the first entry in there, and then push into delta batch delta, something like that. Just put those in there, get it started. And then for each of the other, so there's m things in our, oh, this shouldn't be train data, this should be batch, sorry. There's m things in our batch, so for I equals 2 to mini batch size, or m. So we already calculated the output and inner errors for batch 1, so we're starting at 2 here. So I'm going to say a comma, I can just copy this, paste it. Now place this 1 with an I, make sure the spacing is correct. And then just push in here. I guess I could have started at 1 and just kept on pushing in there, but it's fine. This will work too. All right, so that collects all of the errors for a given batch. And now once we have that, we can update our weights and biases. So for L equals to L minus, L decrement by 1 down to 2, we want to update our weights. So network dot W minus equals, I almost forgot, we need a alpha, a learning rate. So this is going to be alpha divided by mini batch size times the sum of, so delta batch I at layer L times a batch I at the L minus 1, so the previous layer, right? Transpose for I equals 1 to mini batch size. So this right here is just the sum from the slide. So if we look at our slide here, that's what this is here. The errors times the post-activation of the previous layer transpose. So the errors times the post-activation at the previous layer. Okay, so now we need to also do this with our biases. So let's change this to B. And then here, we don't multiply by the coefficients. We just have coefficient 1 there. And. All right, so this function here doesn't return anything, and that's, this exclamation mark just means that we're changing the network here. All right, so let's just run this. So I guess this will be for like epochs. We can choose whatever we want to test it out. So for underscore equals 1 to 100, mini batch update exclamation mark, our network. Mini batch size, we'll choose like a size of 2. We'll use our train data, and then we'll pick alpha to be 0.4, something like that. Oh, not network. We're using the same network we had above. It could be a random little, oh, here, see, mini batch size dataset. So well, I passed in a network for some reason. This should be data set. Somewhere there's size L. I doubt this is going to make a difference. Let me just see size of network dot W. That should, somewhere there's a small error. Hold on, let me see. Copy there. something. Yeah, there was just somewhere there was a small error. Not sure where it was. But this is the code. Ignore this. This is just me specifying specific types. Actually, I'll go ahead and leave it there so you can see it. So the double colon just specifies that this network is the neural network type. So Julia knows. Mini batch size is going to be an int64. Dataset has a complicated type. I'm not going to put that there, but alpha is a float. So now let's see what our success percentage is. We barely trained this thing at all, so I'm not assuming it's going to be too good. So let's see if this increases a little bit on the test data. See, it went from 10 to 20, and we're only like, let's just run this seriously 10,000 times. Let's see. All right, so that's pretty quick. Yeah, we're already at 62%. Let's do it again. So we've run it, what, roughly 20,000 times, taking a few seconds. At 65. Let's go one more time and see what happens. 65 is already pretty, we're getting somewhere, right? %78 accuracy. So I'm gonna do this 60,000 times, right? And while that's running, I'm gonna get a nice little function to visualize what we're doing. So it's still running. So I'm gonna write a quick little cell to visualize our output. Where is the... All right, so that finished. I don't know if that did much, but let's see the 84%. That's pretty good. I'm gonna run it one more time. It's like 10,000. So in my experiments with this network structure of a, so if we recall, where's my network? We have 3 hidden layers with 100 neurons each. With my experiments, I found that doing mini batch sizes of test of size 2 and a somewhat high learning rate seem to be, let's just see what happens if we take a batch size of 15. Let's decrease this. Let's play around with it. So again, let's see, 85. Oops. If you play with this enough, you can get it to, so let's just say, let's look at some random examples. Rand, say, from x for x equals 1 to 10,000. How many things are in the show test example? So there's 10,000 test examples. We'll pass in our network, pass in that random I, and then test data. So there. And we see that we have got some fairly decent results here, just anecdotally, just kind of testing it out. We see that our predicted label and the actual label tend to match up. That one was a 4. We predicted a 4, but it was a 2. But again, we only have 85% success right now. Let's run this again and see if we can get it a little bit better. So again, playing with the batch size and the learning rate is going to go a little bit better. And we can see that it's doing okay. It's not great. So after class last time, I was able to play around with the hyperparameters and get up to 94.3% accuracy. And if I'm almost positive, if I kept on, like if I did this 60,000 times, and sort of like maybe decrease the learning rate a little bit, you'll find that as you get higher and higher percentages of accuracy, you do want to decrease and change your learning rate. So let's just see if there's any success here. If we can get up to 90 before the end of class, it's running 60,000 epochs on training batches of size 15 with learning rate 0.04. And I'd like to emphasize, now that we've kind of gone through all this code, that this is only one way to do it from scratch. Like, I've programmed this several times on my own, and I think that every time that I program it, it changes a little bit. For example, I think this is the first time I created my own neural network type using mutable struct to store the weights and biases. But there's just many, many different ways to do this. If you were programming this in Python, you probably want to make a neural network class with class methods, including update and functions that operate on that class. So that's something you probably see online if you search around for neural networks from scratch using Python. So this is still running. I'm not sure if it'll finish in time. But given that we've already made it to 85% and we've run it for a few seconds, like to me that means that we're on the right track, and eventually through playing with hyperparameters and mini batch sizes, we could get this up to 90% accuracy or even higher. I think the highest that I've ever gotten it on my own was something like 97-point-something% accuracy on the test data. So with that being said, I think that I will give extra points at the end of the semester to whoever gets the highest classification percentage on the test data, writing a neural net from scratch in Julia. So I'll look at everyone's percentages, and whoever gets the highest percentage will get some bonus points for that directly on your GitHub account. Another thing that you might want to do when you're constructing your notebooks for your directory on neural nets from scratch in Julia is to make plots on the cost function and the error according to mini batch size and learning rate, and try to figure out on your own what works best. So you have mini batch size and learning rate, but then you also can change the network architecture, right? Like I kind of chose 100, 100, 100 hidden layers arbitrarily. You can change this to like maybe 500, maybe 50, I don't know. They don't have to be the same. You play around with it and you experiment with it and see what you can get. Okay, so this is still running. I'm just going to let it run. If it does really well, I'll let you know on Blackboard. But I think that'll be it for today. So everyone stay safe. I will upload this video to YouTube after it renders. All right. I will see you all next week.